All right, welcome back. We're here continuing our discussion of the addition reactions of aldehydes and nucleophilic addition reactions to aldehydes and ketones. All right, so where we're going to jump in next is with the Wittig reaction. All right, so the Wittig reaction is named after the German chemist George Wittig. All right, so it starts with a W. So being a German name, it has a V sound. So Wittig is the way to pronounce this. And it's a two-step reaction where we have to make something called a phosphorus ylide. Right, that is a strange word. It's spelled Y-L-I-D-E, ylide. Right? And we're going to make that by reacting an alkyl halide with triphenylphosphine. All right, so phosphorus, hadn't seen it much, but it is a group 15 element, and it's right underneath nitrogen in the third row. All right, so it will be nucleophilic in this case, where we have these lone pair electrons that are going to come in and do an SN2-like attack on our alkyl halide, and that's going to make the following compound. And I'm going to clean up my phosphorus a little bit. So phosphorus had 3 phenyl groups. So there we go. I'm going to put the pH there in parentheses and a 3. So that tells me I've got the 3 phosphorus, 3 phenyl groups on the phosphorus. Now, phosphorus, like nitrogen, has 4 bonds and no lone pairs. So that gives it a positive charge, and it'll coordinate to the chloride here. So, in the next step, this phosphorus-containing compound is going to be treated with a strong base, such as N-butyllithium. But I'm just going to draw B like so for just some generic base that we're going to use. Depending on your solvents, you can use different bases. Like I said, N-butyllithium is the typical one that's shown. However, we're just going to say, hey, we just have the base. All right, and the base will remove that hydrogen and form a carbon-phosphorus double bond. All right, so now we don't have the positive charge anymore because now phosphorus has 5 bonds. All right, so being in group 15, 5 bonds, that gives it a neutral charge. Now, remember, phosphorus is a row 3 element, so it can valence expand. It can have more than 4 bonds. All right, so the next thing that we're going to do is draw a resonance contributor to the structure. And what I'm going to do is I'm going to move the electrons in the pi bond down to carbon. Now, carbon is more electronegative than phosphorus, so this is totally fine. We usually see carbon moving its electrons up onto oxygen, but this is phosphorus. All right, so now we see a negative charge on our carbon, and that tells me it is nucleophilic. So the business end of this molecule is right there. All right. That is the nucleophilic part, and these are resonance contributors, so you can draw them in either form, doesn't matter. But what we have here is the phosphorus ylide. Both of those guys, all right, are the phosphorus ylide. They're resonance contributors, so they're the same molecule. They just are shown in 2 different forms. I prefer this form here because it shows the negative charge on the carbon, all right, and it really makes me think that it's a nucleophile. All right, so what we're going to do now, we're going to take a ketone, let's take acetophenone, and I'm going to react it with my phosphorus ylide. All right, so step 1, nucleophilic addition, like we've seen 100 times it seems. All right, so all we're doing is we're taking the lone pair electrons of the carbon and attacking the carbon on the ketone, like we've seen many, many times before. So what do we get here? I'll start down here. And what have we added? All right, so looking back, the nucleophile was carbon. All right, so carbon is what we have. All right. You know what? I'm going to back up just a bit. I don't want to put my methyl there, and I'll show you why in a second. I'm going to put, oh no. How about we just, there we go. I'm still learning. All right, oxygen there, and then my carbon, and then my methyl down here. All right, so I just want to show the carbon and the oxygen near each other. And the reason why is I'm going to need the phosphorus and the oxygen to be in very close proximity to each other. All right, so phosphorus with a plus charge there, oxygen with a negative. All right, phosphorus, and let me clean that up. All right, better. All right, so phosphorus and oxygen love to make bonds. So you got one with a negative charge and one with a positive charge. Boom, that's going to happen. All right, and the reason why is just one of those bonds on the periodic table that is just really, really strong. Like the silicon and fluorine bonds are very strong. The phosphorus and the oxygen bonds are very strong as well. So we make this four-membered ring. Not this one over here. All right. So oxygen there, carbon with two hydrogens and a phosphorus, and oxygen and phosphorus are bonded to each other. We've got the three. Believe me, there's a three over there. And I'm off my screen. There. All right. So phosphorus goes back to neutral. It's got its 5 bonds. Oxygen goes to neutral. It's got its 2 bonds and 2 lone pairs. All right. So oxygen loves making bonds with phosphorus. Why not have another one? All right. So the way we're going to do that is by this arrow push here. All right. Where we're going to make a phosphorus-oxygen double bond. And then phosphorus is just going to take off with the oxygen. All right. And leave behind a carbon-carbon double bond. All right. All right, so what's changed? Well, look at this. All right, the oxygen has been traded out for a what? A CH2 group. Where did that CH2 group come from? Right here. All right, so what we're going to be doing in the Wittig reaction is we replace the oxygen with a R group. All right, so let me clean this up a little bit and show you what I'm talking about. So if we go back to acetophenone, and we now take our carbon, all right, what are we going to be doing here? We're swapping this oxygen with this carbon, all right, and what comes with the carbon? Not the phosphorus, right? The phosphorus makes off with the oxygen. All right, and what we do is we have the carbon attaching where the oxygen was, and it brings these two groups, whatever they are, with it. All right, so we can kind of clean this up and go back and say, all right, what am I going to attach to this phosphorus? A carbon, right? 2 groups here. We can make them methyl groups if we wanted. All right. And what are we adding? Oxygen is going away, and we're adding this. All right, carbon with its 2 methyl groups. So what does that look like? Redraw the molecule without oxygen. All right, I just redrew it without oxygen. The double bond's still there, but no oxygen. Plug in the carbon that's attached to the phosphorus, and then whatever's other 2 groups were on that carbon go on there. All right. Maybe if I could draw them correctly. There we go. All right. So that's the Wittig reaction. Easy peasy, right? Okay. Practice, practice, practice. Next one I want to look at is the addition of primary amines to aldehydes or ketones. And what's going to happen here is we need to look at amines for a second. So amines are organic molecules that contain nitrogen, and depending on what level of substitution of the nitrogen you have, we have different types of amines, just like in alcohols. Right? This would be a primary amine. All right? Notice I don't even look at the carbon that's next to the nitrogen. I just look at how many carbons are on the nitrogen. That's a little bit different with amines. All right? So on an alcohol, you don't have but one carbon group no matter what on the oxygen. Nitrogen, you can put as many as 3 carbon groups. So this would be a secondary amine. And finally, we can have tertiary amine, where all the groups attached to the nitrogen are carbon. All right, so primary, secondary, or tertiary. And the ones we're going to be focusing on is the addition of primary amines to aldehydes or ketones. All right, so let's go with, let's do an aldehyde this time. And I'm going to add something called methylamine. To this. All right, now to be frank, the amine in this case is not nucleophilic enough to attack the aldehyde. All right, so we need a little bit of acid around to push this reaction. So we're going to add mild acid here. Now H3O plus is a strong acid, but when I say mild acid, it means the concentration isn't so high that the pH is super, super low. We're talking somewhere around a pH of around 5. All right, with this H3O plus here. So step 1 is going to be protonation of the ketone. And these are all reversible steps. Oops, I don't have that bond yet. Okay. All right, just protonated my ketone with H3O plus. So now we have H2O as the conjugate base. Now the methylamine can attack. All right. And I'm going to go to the next page, but what are we doing here now? This is what we've seen several times, right? This is just the acid-catalyzed addition of a nucleophile to a carbonyl-containing compound. So what we've added is the nitrogen atom, all right? So let's go to the next page. All right, so nitrogen has now been attached to the carbon, all right? So just to go back, the new bond we're making is the carbon-nitrogen bond, all right? This compound here is something called a tetrahedral intermediate. They aren't stable, all right? So what's going to happen here is this guy really wants to get back to where it came from, all right? So it wants to go in reverse, or it wants to turn into something else, so it wants to go forward, all right? It doesn't really want to stay in this form. And the reason why is because carbon is really being shredded by some electronegativity. So you got an oxygen pulling up on it, and you've got the nitrogen also pulling. And to make it worse, the nitrogen's positively charged, which means it is really electron poor in this case, and it really wants to get those electrons back. All right, so one thing that's going to happen is the water is going to act as a shuttle for a little thing we call a proton shift, all right, or a hydrogen transfer. All right, so we put the or get the hydrogen off the nitrogen. And we have H3O plus up here again. And now oxygen is going to grab this proton. And like I said, it's shuttling the proton. And we have to do it this way because we are an acid, all right? And if you are an acid, a tetrahedral intermediate will only collapse if there is a protonated group on the tetrahedral intermediate. And in this case, that protonated group was, it was nitrogen. And in the case at the bottom of the page, the protonated group is oxygen containing, all right? So it will be our leaving group, all right? So nitrogen is going to come in here and shove out our oxygen. So we're going to make a nitrogen-carbon double bond. Here. All right. And this compound right here is a iminium ion. All right. We can use the water that was just kicked out Oops, these are reversible. To make the neutral organic product. There. This is called the imine, or something called a Schiff base. That's an older term. Most people would say these are imines. All right, so I-M-I-N-E is an imine. So let's recap this. So if I were to take acetophenone again, and if I were to take methylamine, and mild acid, what am I going to do? Well, I'm going to take this oxygen off and replace it with nitrogen. All right. So much like we saw in the Wittig reaction, we draw everything but the oxygen and put the nitrogen there. All right. And our nitrogen is going to be an iminium, or sorry, an imine. It loses 2 hydrogens in this process, right? Because think about it. If oxygen's leaving, what does it leave as? Water, right? Where did those 2 hydrogens come from? There. All right. So what we do is we just swap out O for N, take 2 hydrogens off the nitrogen, and the nitrogen's got 1 thing left on it, and that's what we see here. All right, so that is the end of this video. We have now completed all of our addition reactions except for the addition of alcohols to carbonyl containing compounds, and we'll look at that in the next video. All right, thank you very much.